All right, welcome everybody to this week's GOCC. We're very happy to have Nick Anderson, who's going to be telling us about extremal matchings on plabic graphs from height functions. Before we begin, I'd like to remind everybody of our community statement. We are all learning, everyone has something to contribute, and no one has all the answers. So with that being said, Nick, take it away.
All right. Well, yeah, thanks for having me. Yeah, as Joe said, I'll be talking about extremal matchings on plabic graphs from height functions, and this is joint work with my advisor, Greg Musiker. Um, so to begin, the outline that we have for today, we're going to start talking about height functions, some of the history, main definitions, and a main result, just to get us a kind of hand wavy picture of what are we building towards. But then we have to really jump back and discuss three big topics of background information: the combinatorics of positroid cells or positroids. Um, we have to discuss about plabic graphs, and then we can introduce what matchings are and a lattice structure that we can build from those. And then we can go back to building in more detail our main results on height functions that we're going to use. So historically, height functions were introduced by Bill Thurston in 1990 as a study for Lagrange tilings, and these were um, height functions were giving physical altitudes to um, these objects, these regions. Just a few years later, Propp linked these to matchings on planar bipartite graphs. And this is this recently published work. I think this was just published last November. Um, and then in the current work, we use these to construct these so-called extremal matchings on a specific case of plabic graphs. So to kind of, again, a little bit hand wavy defining height functions, but if we have a planar bipartite graph H with faces f of h, black vertices b of h, and white vertices w of h, we can define a height function to be a function on the faces that gives some sort of real valued assignment, um, such that at each white vertex, or we can consider black vertices, but we only need to consider one of these two. Um, we see this picture, this local picture where we have face labels f1, f2, all the way to fp minus 1 and fp. But our height function is decreasing as we go counterclockwise about our white vertex. Um, and at some point, we're decreasing, 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 but we get back to where we started. So then we're going to have this natural break where f1, the height function output of f1 is greater than the height function of fp. Um, it's pretty natural to associate these with matchings. So in particular, when we kind of consider this picture that we had in this definition of a height function, um, we can match an edge, or we get a matched edge for each time we have this break in monotonicity or in this decreasing of height functions. So as we traverse our faces counterclockwise about our white vertices, we include the edge exactly between the two faces where that monotonicity breaks. Um, and so our set of height functions up to what I'll call monotonicity preserving transformations are in bijection with matchings. So then what can we do with that? In in what I hope to get out of today is that we can define this new family of height functions, which I'll call fundamental height functions, which are indexed by j through 0 to n minus 1, um, where essentially these are defined by summing over the face label entries that we can have on our plabic graph G. Um, One of the ways that we'll be able to combine these fundamental height functions is through the so-called translated maximums, translated minimums, which I'll denote by Tmax and Tmin with some list of our fundamental height functions. It turns out these are also height functions, so they also correspond to matchings. And the main theorem, main result that we have is that when we take these translated maximums of fundamental height functions, this corresponds to our minimal matching. And when we take the translated minimum, this corresponds to our maximal matching. And just as kind of a brief overview, we don't have to see or necessarily know even what this ordering looks like. But we get this lattice structure where left is least, left is minimal, and to the right is maximal. And this is one example where we can build our Tmax with these two specific fundamental heights. Um, and also we can, if we have a target labeling on our plabic graph, we can build the maximal matching with this Tmin and kind of construct the poset downwards. But yeah, so that's again, like I said, an overview of our results, but really to back this up, we have to go to the combinatorics hiding behind um, these matchings or behind these spaces. So um, in particular, we're interested in these positroid cells within the Grassmannian. So we have our Grassmannian, which is our space of k-dimensional subspaces of Rn. For each of these, for each subspace, there's a matrix that's a k by n rank k matrix um, defined by our subspace is the row span of this matrix. Um, One embedding that we care about is this Pluker embedding, where if we consider the column vectors of our matrix A, our point in the Grassmannian, we get these Pluker coordinates, which are the k by k maximal minors of A, where the index I is some k subset telling us which column vectors to choose or include in this minor. And just a kind of brief refresher on linear algebra, right? If our determinant is non-zero, if our k by k minor is non-zero, then those column vectors form a basis of Rk. Um, so this is kind of the flavor of what we're looking at. Um, Now, for each point in our Grassmannian, we can define what's called a column matroid by looking at what k subsets of n correspond to non-vanishing Pluker coordinates for this point in our Grassmannian. Um, and this gives a nice stratification of the Grassmannian in some way. And then we can consider the totally non-negative Grassmannian, which is a subspace of the Grassmannian where we cut out any Pluker coordinates which evaluate to negative values, or we cut out points who have Pluker coordinates evaluating to negative values. Um, in this case, when we consider the column matroid for a point in our totally non-negative Grassmannian, then this is what we call a positroid. Um, this it's a it's a matroid with totally non-negative representation, meaning its maximal minors are totally non-negative. Um, and then the positroid cell is exactly the collection of all such points in our totally non-negative Grassmannian, which have the same positroid P in this case. And this then gives that the totally non-negative Grassmannian is stratified by these positroid cells. Um, and so that kind of defines the space that we're interested in. And we really are going to dive into the combinatorics of these so-called Pluker coordinates, which define our positroid. Right. So as an example, we have this matrix B, which is a 3 by 7 matrix. I'm claiming that it lives in the totally non-negative Grassmannian, GR37. Um, and if we were to want to determine what this column matroid is corresponding to B, or this positroid corresponding to B is, you might naively start like computing some of these maximal minors, right? If we take the determinant of the first three columns, we get 1. If we take the first, fifth, and seven, we get one. Um, if we take the second, fifth, and seven, you could verify um, that we get three. But if we take the second, third, and fourth, we end up getting zero, um, and so on and so forth. And I've included a few more. But it turns out there's seven choose three, so 35 of these maximal minors to check. And hopefully there's a better way of figuring this out. It does turn out that these are the two that I've shown that are vanishing are the only two. So when we take this like complete uniform matroid, um, the only two K subsets we have to throw away are 1, 6, 7, and 2, 3, 4. But there is some data that gives us um, that can kind of ease that calculation. So I have this brief graphic of um, some of the combinator or some of the bijections that we can expect here. So we already kind of defined positroid cells. We're going to move on to Grassmann necklaces, decorated permutations, and then plabic graphs. And there's a lot of the bijections here are due to Postnikov or are introduced in Postnikov's preprint paper, with the internal ones, that internal line related to these two papers as well that biject plabic graphs and Grassmann necklaces together. But yeah. So defining Grassmann necklace and reverse Grassmann necklaces, these are sequences of K subsets which satisfy these exchange relations. And the exchange relations themselves don't seem like they're pretty harmless, but they're not very intuitive on their own of what they're doing. If we have the index I in the ith term of a Grassmann necklace, then we trade it out for some new thing, J. Um, and if I was never there, then we don't trade it out at all. Um, and that's kind of the two rules set or giving our recurrences on these Grassmann necklace and reverse Grassmann necklace pieces. Um, One way we can better understand how these or we can better understand these Grassmann necklaces is to look at the shifted linear order on the numbers 1 through n, which I'm going to call the A ordering. Um, it's basically saying that we can choose A to be the smallest value of the numbers 1 through n. And we cyclically increase up to A minus 1, taking this mod n. Um, And then we can extend this linear order to a partial order on K subsets of bracket n. So if we have two such subsets, I and j, we can compare them component-wise, where we've ordered um, the sets I and j with respect to this A order. So we say that I is less than j under this A order, if and only if component-wise IL is less than JL under the A order for all L. All right. So geometrically, these Grassmann necklace and reverse Grassmann necklaces have a little bit more meaning. So if we go back to a point in the totally non-negative Grassmannian, um, and we have the column vectors vi, um, the Grassmann necklace is a sequence of A minimal bases. So that means that the eighth Grassmann necklace term indexes the A minimal basis of Rk formed by the column vectors vi. Um, and similarly, the reverse Grassmann necklace is a sequence of A plus 1 maximal bases. So the eighth reverse Grassmann necklace term indexes our A plus 1 maximal basis of Rk formed by the column vectors Vi. Um, and then the theorem that kind of links this back as a bijection with our positroids and positroid cells is that if we're given a Grassmann necklace, then we can define this set of K subsets of n where we include an element if and only if it's greater than each Grassmann necklace term, each eighth Grassmann necklace term under this A ordering. And the same is true dually for it has to be each subset that we include has to be less than the eighth reverse Grassmann necklace term under the A+1 ordering. But yeah. So an example related back to our matrix B that we looked at, um, we can now this is saying to define what this positroid corresponding to B is, we really only have to look at the Grassmann necklace or reverse Grassmann necklace terms. We only have to find a sequence of seven A minimal bases or seven A+1 maximal bases. And here they are listed out, right? If we read along columns, we hit 1, 2, 3, that's a basis, we're good. We tried 2, 3, 4, that was 0, but we get 2, or we try 2, 3, 5 as a Plücker coordinate. And we get that as our second Grassmann necklace term. And then we can continue on, right? 3, 4, 5, 4, 5, 6, 5, 6, 7. We would try 1, 6, 7, but we saw that was 0, so we try the next smallest thing, which is 2, 6, 7. Um, and that builds out our Grassmann necklace. And we can note, as in the bottom here of the slide, if we look at those Plücker coordinates that were vanishing on our point B, um, they're exactly the ones that are falling kind of of this um, outside of this set where they're either smaller than a Grassmann necklace term under some A order, or they're greater than a reverse Grassmann necklace term under some A order. Right. Were there any questions so far? Okay. So then um, the next kind of object that we wanted to biject with Grassmann necklaces were these decorated permutations. So I'll call this pi tilde, and it's a pair of a permutation from Sn along with a coloring function on its fixed points. So to write this in one line notation, um, it's typical that we choose, like if we have this fixed point where I goes to I, and we color I with a 1, we'll write pi tilde of I as overline I. Um, and if our coloring function sends I to -1, we'll send pi tilde of I to underline I. And it maybe takes a little bit of convincing yourself, but not too terribly much. So each time we have a Grassmann necklace or reverse Grassmann necklace, we get a decorated permutation that's corresponding to that. And I've written that as like pi of our Grassmann necklace or sigma of our reverse Grassmann necklace. And these are exactly coming from that exchange relation that we had. So if our Grassmann necklace in this, if our ith Grassmann necklace has an exchange relation and exchanges the entry I for some j that's not equal to I, our decorated permutation sends I to j. It's not a fixed point. If our Grassmann necklace it takes away the ith thing, but it also j is equal to I, it re-includes this I, then I gets an overline I. And if I was never in this ith Grassmann necklace term, then we get underline I. And very similarly for um, the reverse Grassmann necklace, it's based kind of the same relations, just a different exchange. And I'm going to black box this for now, but there are bijections between decorated permutations and Grassmann necklaces and inverse decorated permutations and reverse Grassmann necklaces, as we'll see in our following example. So we can revisit the Grassmann necklace Grassmann and reverse Grassmann necklaces that we set up before, and we can just look at the exchanges that happen. So as I move from the first Grassmann necklace term to the second, I include a 5. From second to third, I include a 4, then 6, then 7, 2, 1, and 3. And this is exactly what gives me the decorated permutation 5, 4, 6, 7, 2, 1, 3. With the reverse Grassmann necklace, we have the exchange relations happening to the left instead of to the right. but this also gives us this inverse. I guess I'm calling it pi tilde inverse. Um, but this is 6572134. And you may notice that these are like honest to goodness SN inverses. Um, so it turns out that if we have our Grassmann and reverse Grassmann necklaces corresponding to the same decorated or the same positroid, then the corresponding the decorated permutation we get with respect to the reverse Grassmann necklace is the inverse of the decorated permutation we get with respect to the Grassmann necklace. And so those are related in a very nice way as well. Um, but with that, I think I've added two of our lines in that picture of bijections. So we're going to move on to talking about plabic graphs. So these are planar bicolored graphs G, which are embedded in a disk. I'm going to choose that we have n boundary vertices on our disk, which are numbered 1 to n clockwise, and all of these boundary vertices are colored black. Um, I'll denote kind of standard. The faces are f of g, edges e, vertices v, and I want a proper two coloring on my graph. So I have black and white vertices that are bipartite. Um, and we'll say this property that J or our graph G is of type Kn if we have the relation on the number of black and white vertices. It's the number of black vertices is equal to the number of white vertices plus this n minus k factor. In this case, the n and k are coming from exactly the Grassmannian GRKN. Um, yeah, and we're going to make one technical assumption that G is always reduced, but we'll have a way of testing that in just a couple slides that we'll introduce. So one of the things we can do with our plabic graph is we can add these Postnikov strands or these zigzag strands. I'm going to call them strands, um, but these are coming from each boundary vertex, and they traverse the edges of our graph following some rules of the road, and then they end at another boundary vertex. Um, so the rules of the road being that as we approach a white vertex, we turn maximally left, and as we approach a black vertex, we turn maximally right. And so you can pick out your favorite strand in color coordinating and see like, okay, yes, these do in fact follow those rules. For example, maybe this like kind of darker blue. I turned left at a white vertex, right, left, right, left, right, left, and we ended. So we went from 3 to 6. Um, One thing that's allowed for us is when we start and end at the same boundary vertex in our reduced property. And what that looks like, there's two scenarios. We'll have something called a black lollipop at our boundary vertex I if the leaf part of the graph is a black colored vertex, and we'll have a white lollipop at our vertex I if the leaf part is a white colored vertex. So then a very natural thing we can do is arrange these strands into what's called a trip permutation. So we'll record where the strand starts and where the strand ends. So um, in our trip permutation, if a strand starts at vertex I and traverses edges and ends at boundary vertex J, where J is different from I, then we write that pi I goes to J. If we have a white or black lollipop, then our trip permutation has a fixed point, and we decorate white lollipops with the overline and black lollipops with the underline. And so, in particular, this definition of a trip permutation gives us another decorated permutation, which we said decorated permutations via their correspondence with Grassmann necklaces correspond to some positroid P. And um, I guess I'm sweeping some things under the rug, but G is the trip permutation is one of the invariants of G under some well-defined local moves. And so G also corresponds to the same positroid P as its trip permutation. Um, if we think back a couple slides, the picture of um, The decorated permutation coming from our Grassmann necklace is exactly the same one as this trip permutation that we've got. Um, and if if our decorated permutation corresponding to a positroid and our trip permutation corresponding to a positroid are the same positroids, um, it can be shown that the um, decorated permutation is the same as this trip permutation of G. Yeah, so this is kind of the first application of strands that we're going to use. We have a couple more. The next thing that I want to introduce with respect to our strands is a type of edge labeling that gives rise to this resonance property of Kodam-Williams. Um, so if we have an edge E where the strands crossing E are the strands starting at I, the strands starting at J, we can label this with like curly brackets IJ. And when we want to care about the order of I and J, we write square brackets with I comma J if I is less than J. If J were less than I, we'd reverse the order in those square brackets then. Um, we then can say that G has the resonance property if at each internal vertex we see the edge labels square bracket I1, I2, I2, I3, all the way IM minus 1 to IM, and then I1 to IM. And we see those clockwise about our vertex V, and the as we increase in the index of I, we're increasing. So I1 is least all the way up to IM. And then the main theorem, again, going testing for this reduced property is that G is reduced if and only if G has this resonance property. Um, and this is one of those things that we also can label our edges of the graph with respect to where the strands are ending. So I gave it kind of in the original definition, but there's no harm in um, looking at where our strands end and labeling edges in that way as well. We'll see an example of this come up in just a sec. The last thing we can do with strands is we can introduce face labels of G. Um, and so there are two main conventions. We have source labeling and target labeling. We look at where in source labeling we look at where a strand starts, and every face that lies to the left of that strand receives the label I if it starts at vertex I. In target labeling, if a strand ends at vertex I, every strand to the left of this strand, which is likely different from in target or in source labeling, also receives the label I. Right? With the one caveat, if we have these fixed points, if we have black or white lollipops, um, a white lollipop tells us that every face on our graph has the label I, and a black lollipop at I says that no face on our graph has the label I. Um, so for example, I've included the source and target labeling along with our strands of of the kind of underlying graph that we've been looking at. And if I follow that same strand, let's see, the one that started at 3, I think it was, that goes from 3 to 6, every face kind of in this, I guess it kind of looks like a cowboy hat, but every face there contains the index 3. And you could check all the other 6 strands and see that same thing happening. If I go over to the target labeled version, um, again in the same region, that strand now ends at 6. So every face in this same cowboy hat region ends with or includes the face index 6. All right, so that was a lot of information of like what can we do with strands. Um, I want to give an example of why I want all three of these things with strands. So it's a lemma to show that as we go, as we look at any white vertex, we could again dually define this for black vertices, but I think it's easier to state in terms of white vertices. Um, as we look at each white vertex, the faces around that white vertex or incident to that white vertex are labeled by some common like k minus 1 subset of n plus some other singleton that's changing. So every face around any white vertex has some like k minus 1 subset of face labels that are the same. And then there's exactly one face entry that's changing. Moreover, if we go counterclockwise about this white vertex, there's an ordering such that the face labels are decreasing. Um, and this is what kind of in blue, this is what we've called this almost monotonically decreasing property. And so this mapping on the singletons of face label entries satisfy this. And if such a mapping is an honest to goodness function, then this is what we're defining as a height function as well. So in this case, the picture is kind of my proof of this. So if we use this resonance property and remember that the labels for the faces come from the strands crossing, a strand comes in and takes a left. So for example, this is the strand I1. It contributes the face label I1 to its left. We can do the same for each of these. So the singletons that are listed on my so-called faces in this local picture um, correspond to the I1, I2, I3, and I4. And the resonance property says, well, I4 has to be the greatest of these. And then as we traverse counterclockwise, we get exactly the ordering that um, we're hoping for. Yeah. Any questions so far?
Sorry, you said that there's a k minus one subset associated to the white vertex.
Yes, so I'm
W-
suppressing that part of this, but each of these, if I wanted to write out like their face label, it would have some like SW
right.
union
So,
that.
so, so, which is interesting. That means that you have a kind of complete labeling of vertices, faces, and edges by various subsets of different kinds, either by subsets of size one, size two, or size k minus one. Right.
Right, yeah.
Which is
Yeah, and I think it just differs locally, so it's definitely white vertex dependent. So like if I had a different white vertex over here, it's not the same, like this might have SW, but this has some SW prime, for example.
no, no, right, right. But still, you have some way of labeling all of the white vertices with k minus one. Just an alternative way of labeling a Postnikov diagram, distributing all of the labelings kind of equally, among not just on faces, but just on edges and vertices also.
Yeah. Yeah. Um, but yeah, so then moving forward, I'm going to start talking about matchings and then how we can apply a lattice structure of matchings. Um, yeah, I guess maybe one last remark that I missed is that, like I said, the this almost monotonicity property of our face labels is exactly what allows us to define height functions. So this at this point we are ready to like define height functions, but I want to give us a little bit more time to talk about the poset structure that we want to assign to matchings. Um, so we'll start there first. Um, so remember that if we have a graph G of type Kn, we have this condition of more black vertices than white vertices, and so an almost perfect matching on our graph G, which we'll call M, is some subset of edges such that each internal vertex is incident to exactly one edge in our subset M in our matching. I'll denote this by highlighting edges, but because of this uh, exceedance of black vertices to white vertices, then we have to make a choice of k matched boundary vertices. And this is what we'll call the boundary condition of our matching. And we denote the set of all matchings with the same boundary condition as this like mathcal m sub I. So the example that I have here is just a matching with the boundary of 2, 5, and 6, right? And all other boundary vertices are unmatched. All right. So in the current picture of like all these bijections that we set up, we never really linked the plabic graphs back to the positroid cells. We kind of did this loop, and I think I'd be leaving something big out if we didn't actually do that. So the way we can make that last bijection is through this boundary measurement map that Postnikov introduced. And so our inputs that we're going to use is a plabic graph G, a positive edge weighting, and then this partition function, which I'm suggestively calling delta I of G, which is our partition function on the set of all matchings with a fixed boundary I. Um, and so the statement, which here I'm using a statement that's more similar to lam, um, but the collection of the coordinates delta ig for all I and as k subsets of n defines a unique point x tilde in the affine cone over the positroid cell, such that the partition function matches up um, with the Plücker coordinates on this point for every I. And conversely, any point um, in the positroid cell is realizable as some plabic graph, right? And so how does this come about, or how do we work with this? In our running example with this matrix B, um, one thing we can note, if I consider the matchings with a boundary condition 1, 5, and 7, there's only one of these guys. There's no way I can like make another one after making these choices. I have to include, say, these edges, and then for degree reasons, I have to include this guy, then this guy, and so on and so forth. And there's just no choice. If we weight all of the edges with 1, then essentially the delta i's of g's are telling me how many matchings do I have with this boundary condition I. It turns out that that's the same as the Plücker coordinate of this matrix B when I take 1, 5, 7. Now, what happens if I try to take the matching with boundary condition 2, 3, 4? Well, I have to include all of these like two valent white vertices that live there, and because of degree conditions, I have to include this guy. But now I have an issue at this like white vertex, right? I have no edge that I can include in my matching. And so this corresponds exactly to a vanishing Plücker coordinate as well in our positroid. And so the theorem says we can really realize positroids um, as the set of boundary conditions which lead to non-empty sets of matchings with those boundary conditions. And so that completes kind of the diagram we had. So now I'm going to switch to this partial order that we can place on matchings. So one thing you might notice is if a matching contains exactly one half of the edges at any face, then we can swivel, or what we'll call swiveling, we can swivel that matching at the face to obtain a new matching M prime such that the boundary condition is preserved. Um, in this case, I've shown this locally for a square and for a hexagon. And I'm going to define the order that if we look clockwise about the face, so I've oriented all of the edges, but if we look clockwise about the face, I can swivel up if my edges are white to black, and I can swivel down if my edges are black to white. And that's the same over here. If I orient my edges clockwise about the face, all of the edges on the left-hand side are white to black, all of the edges on the right-hand side are black to white. Um, so then to get to the statement of lattice structures, Propp says that under this partial ordering, the set of mixed dimers of type D which is a little more general than what we're considering here. But then on arbitrary finite planar bipartite graphs H, this forms a finite distributive lattice. Um, what we are more interested in this setting is this result of Muller and Speyer, which says when we use the same partial ordering and we consider the set of matchings with a fixed boundary I, where I is some boundary condition that's matchable in our positroid, this assembles into a finite distributive lattice, um, which for us says that the set of matchings with a fixed boundary has a unique minimal and unique maximal matching. And we'll denote these by m minus and m plus, and we'll characterize these guys by if we can swivel m minus, then the swivel has to always be an up swivel. If there's any swivels we can apply to m plus, these swivels always have to be down swivels. That's kind of the mantra we'll have running of how of what these extremal matchings are. But yeah, so just an idea of our picture of what this looks like. This is revisiting the lattice that we had at the start, but I don't have all the decorations of heights and face labels and all that jazz. But here we have the set of matchings with boundary 256. On the left, I have my minimal guy. And if we look, the only faces we can swivel are these ones I've labeled X and Y. If we go clockwise about either face, the edges are white to black. And so those are up swivels. Alternatively, if we go to the far right where we have our maximal matching, the only face we can swivel here is this hexagonal one. And in this orientation, the edges are black to white. And so this is indeed our maximal matching that we can have. And I've included along the way like which faces are getting swiveled by these labels X, Y, and Z. Any questions on the partial order or how this swivel stuff works?
Just partial order, is the partial order going to be distributive if you drop the this reduced condition on the bipartite graph? If you kind of exit the realm of plabic graphs and allow for non-reduced structures.
Yeah, I'm not entirely certain. I haven't quite. I like to work in the nice world of
Mhm.
reduced.
So, but Propp needs that assumption. And that's, I guess, my question.
Um, in the prop statement,
Yeah.
there's Propp does this slightly more generally of just saying like any planar bipartite graph.
Okay, so maybe it can be
So it's not even necessarily like that it's um reduced in the sense of like Postnikov.
right.
Um,
Okay.
but yeah. Um, but yeah, so with that all, we're back to height functions. And so we can recall this rule of our height functions are these like almost monotonically decreasing um, functions, which they, as we traverse faces counterclockwise about our white vertices, we hit exactly one spot where we're walking down a spiral staircase, and then we've come back to where we started. And so we have to build our wall or put our matched edge there. Um, so the family of fundamental height functions that we want to define, where we write these as phi j, where j ranges from 0 to n minus 1, we define these on faces to be the sum of face labels with respect to shifting this cyclic order that we talked about at the beginning. So, for example, if I consider just phi 0, it's easiest to start there. Um, if I take phi 0 on a face f, I'm really summing the face label entries of f. When I go to phi 1, now I'm considering every face label entry of 1 as 1 plus n. So I'm shifting that to be the new maximal thing, and 2 becomes the smallest element of all my face labels. And as I increase j to 2, then I change all 1s to 1 plus n's, all 2s to 2 plus n's, and I get this shifting of that order. Um, it turns out these are height functions, um, and these are what we're going to call fundamental height functions. So then I've included, if we do source labeling, I've included all of these phi j for j between 0 and 6 on the example graph that we've been working with, where my heights are now in red. Um, the So for phi 0 in particular, right, we're just summing over face label entries. We can zoom in a little bit so we can see that, and that should line up. But as we move to phi 1, then now every time I see a 1, it's treated as an 8, for example. Um, and so kind of comparing the two, we see that any face with a 1 now is 7 more, or has a height valued at 7 more. And we'd see that um, same sort of situation as we pass from phi 1 to phi 2, phi 2 to phi 3, and so on. Um, we can consider the same thing with respect to target labeling of our graph. We're kind of always having to bounce between these two conventions. But in this setting, the boundary conditions that we see are different with different j. Um, and I'll just leave that as that because we have a proposition for it. So for so as we range over j, phi j is the only matching that's in its lattice of matchings. That means the the matching corresponding to phi j is both the minimal and the maximal element. It's a unique thing with the boundary condition it has. Um, and when we label G with source labeling, the boundary condition is coming from the J plus 1th term of the Grassmann necklace. Um, for target labeling, phi j gets the boundary condition coming from the jth term of the reverse Grassmann necklace. So in particular, one of those things I'm was kind of throwing under the rug about the bijections between plabic graphs and reverse Grassmann necklaces is that source labeled plabic graphs have face labels coming from reverse Grassmann necklace. So this guy lives over here as a face label, and that's a boundary condition over here, is kind of the moral of what's going on. So the boundary condition 157 is coming from the source labeling of a face as well. Um, and the boundary condition 235 is coming from the face label 235 on the target labeled graph. So there's a little bit of a weird like mismatch that's happening there. Um, but yeah. So then I said we could combine these height functions in some way. So I'm going to define a couple operations of our fundamental height functions or just generically height functions, which I'll call hi. So we can translate our fundamental heights by some value a by just subtracting a from all of the faces. So this is like a uniform affine transformation on our fundamental heights at each face. Another operation that we can do to combine fundamental height functions together, or just height functions in general, is by taking maximums and minimums, where if we take the maximum of a height function or a list of height functions, we consider this on faces as the maximum height achieved over all height functions at that face. And the same for minimums. Um, so these are the three kind of building blocks, and we're going to put them together in one very specific way to get what we're calling translated maximums, translated minimums. Um, so if we take a list of p height functions, so I have phi j1 through jp, and I want to define what's called this translated maximum or translated minimum to be the maximum or the minimum where each consecutive height function we're translating by a successive multiple of n. So I'm taking the maximum for a translated maximum, I'm taking the maximum of phi j1, then phi j2 minus n, phi j3 minus 2n, so on and so forth, all the way down to phi jp minus p minus 1 times n. And the same translation is happening for translated minimums. And it turns out that um, both of these give us a new height function. So we can talk about the matching that's associated to them. So the example at the bottom here, I have phi1 and phi4, and I can combine them in this translated maximum phi1, phi4. Um, and you can notice, like, more or less what this is saying in our example is as long as the face labels of, or the heights of phi4 are no less, or yeah, no more than 7 of the height functions, the heights of phi1, we end up using the height from phi1. But here, for example, we have 27 that we're comparing with 13, and so we end up getting 27 minus 7, 20, coming from phi4. Um, yeah. So these are the candidates. These constructions are the candidates for what gives us extremal and our extremal matchings, right? From the start, we said T maxes corresponded to minimal matchings, T mins corresponded to maximal matchings. Um, how could we possibly? Oh, sorry. Did you have a question?
It's just that I wanted to ask if the boundary condition is changing when you take the max of these fees. It looks like you get different boundary condition on the matching. Is that right?
Yes, yes, yeah.
Okay.
And that's a good thing because otherwise we'd have just like the number of boundary faces in terms of how many matchings we get.
Mhm.
But this is, yeah, somehow combining the boundary condition 2, 3, 5 from phi 1 and 5, 6, 7 from phi 4 into 2, 5, 6. Yeah. Um, and there's more to say of like where that's coming from. Um, but yeah, so if we wanted to know how we could prove that these are indeed height functions, we have to kind of look at how can we compare just two of these fundamental heights that appear in a Tmax or a Tmin. Um, and what we can define as the so-called land bridge of, um, I guess here I'm using phi js and phi jt. So if we have two fundamental heights in some Tmax or Tmin, with a relative translation R, meaning that T minus S is equal to R, um, then we can look at the set of faces where in the Tmax, these things would contribute um, the same value, the same height. Um, Equivalently, if F has our face label I and we let H be the set of the numbers 1 through JT and take away anything JS or smaller, um, a face only appears in a land bridge if and only if the intersection of I and H is of size R. And moreover, I is determined by strands, so we can kind of extend the definition of our land bridge to be determined by strands as well. And so we'll grant this an orientation. We'll grant each land bridge an orientation that comes from the orientation of strands. In this case, the purple arrow is saying like we're entering from the right more or less and exiting out the left um, in this orientation. But yeah, um, so what we can do with these land bridges, I think I'm gonna pass over this in the interest of time, but more or less, or morally, what we're saying is we can use land bridges to define where each fundamental height function is used. Um, like what regions of our graph a fundamental height function is used uniquely. And that's what this picture is saying. So in the example that we saw, um, the fundamental height function phi1 is used kind of to the right of the orientation of this land bridge. And the fundamental height function phi4 is used to the left of the orientation, or to the left of this land bridge with respect to the orientation of kind of going from right to left. Um, the second example is a little bit more involved, but we can see that the F3, F5, and F0 correspond to where phi0, phi3, and phi5 are kind of contributing into this Tmax uniquely. And the land bridges have these kind of either entering or exiting orientations as marked by the green, red, and blue. Um, so to be more specific about our boundary conditions that we can reach here, we need to define one last little bit of notation. So I'm saying that a set of height functions, of fundamental height functions, is source essential if P is the smallest number needed to define the height function T max of that set. And we're going to uphold some relative translations here. We'll do the same thing with T being target essential if P is the smallest number needed to define a T min. So the source essential goes with our T max, target with T min. And again, we're going to uphold some relative translations, right? When I talk about relative translations, typically when we write T max as in T max or T min in these examples, each consecutive fundamental height function is translated by some um, translated by a consecutive multiple of n. So I want to make room for having something like this happen, where I can have my second height function be um, translated by a multiple greater than 1. And so in this case, in these examples, this is definitely swept under the rug, but we can combine in a Tmax, we can combine consecutively index height functions to their least index um, fundamental height function. And the same in Tmins, we can combine consecutively indexed height functions, fundamental height functions to their greatest index height function, and uphold their relative translations in this way. And so I'm going to introduce this notation that's a little bit like a degree shift from like homological algebra in exact sequences. Um, but I'm going to just write this relative translation with a minus multiple of n that it needs to be. And so if we have a source essential set, we can kind of condense this down to a list of p fundamental height functions where each of them, every one but the first one, has some relative translation factor. And if we know our k, there's a unique AP or a unique pth term in this like list of A1, A2, and so on up to p minus 1. There's a unique AP such that the sum over all AI is equal to k. Um, which will be, this is going to be the ingredient that we need to define exactly where our boundary condition is coming from when we do these T maxes and T mins. So the last thing that we want to do is just remind ourselves that the eighth Grassmann necklace comes naturally with this A order. We can order all of the entries from the smallest to greatest, and we define a truncated Grassmann necklace to be just the L smallest or the L A least entries of this Grassmann necklace. And the same for if we have the B reverse Grassmann necklace, we can order these with respect to the B plus 1 order from greatest to least. And we can truncate in a similar way where we take the L greatest entries of the Beeth Grassmann necklace with respect to the B plus 1 order. Then the main theorem is as follows. So in source labeling, so we want to combine source labeling and Tmaxes. When we have this like source essential set in these relative translations in this way, we get the minimal matching, and it has the boundary condition given by these truncated Grassmann necklace terms, where we have just one little shift. So we have J1 corresponds to J1 plus 1, J2 corresponds to the J2 plus 1 Grassmann necklace, and JP to the JP plus 1 Grassmann necklace term. Um, And again, this is the reason why we needed the sum of the AI to equal k, because then that gives us a matching with boundary condition of size k. Similarly, when we think target labeling and we take translated minimums, the the resulting height function of the T-min gives us the maximal matching with the boundary conditions being read from the reverse Grassmann necklace pieces. And then to close this off, I have just the a couple of the examples that we saw on those first slides, right? So here we have the translated max of 1 and 4 that we've been looking at for the last couple slides, which has boundary condition 2, 5, and 6. And we can do these swivels um, on faces like we've been seeing. Swivels on our height functions correspond to adding n to the height. So for example, I'm swiveling the face with a height 14 and I go up to height 21 to get this new matching up in my post set. And I can do the same on target labeled um, plabic graphs, right? So here I can start with the T min of phi2 and phi6 with a translation by 2 to get the maximal matching. And again, swivels down correspond to decreasing the height by 7, or by n in this case. And the last little thing to say is that if we have a positroid with this as the set of boundary conditions that are matchable on its plabic graph G, then the last thing is saying that any minimal matching on a source labeled graph is constructed as some Tmax, and any maximal matching on a target labeled graph is constructed as some Tmin. And so we can construct all of the expected extremal matchings with boundary conditions in our positroid, um, which is a good thing. And that's what I have. So thank you for your attention and your questions. Are there more questions?
I actually had a question. So in you said the positroids are coming there. There's like a matroid hiding in the background, right?
Yes.
And so I'm wondering, is this lattice that you're getting at all related to the lattice of flats of that matroid, or are they sort of two distinct lattices?
I'm not particularly well versed in the lattice of flats for matroid. Um, but I think in um based on a remark of like the Muller-Speyer result that has this lattice structure, is that this isn't something that's been considered, at least at the time, it wasn't considered um too often. But it does give a an ordering on like the positroid itself, on positroids itself.
Gotcha. Okay.
I also have a question. Why are the Grassmann necklaces named necklaces? Are they connected to the usual combinatorial necklaces in any way?
Um, yeah, I guess so they're defined with this like recurrence relation and exchange relation. Right? I don't know if that is the necklace that you're thinking of.
I mean the object that has some n bits and you want to color them and count the different classes and things like that. And it had the connection with
Oh,
Grassmannian. And that's why
yeah,
I'm
I don't know clearly that that has that type of connection.
okay. Yeah. Okay. Thank you.
But just to clarify, so you have these special matchings coming from these height functions, if you like, and they're shifts. They're kind of negative shifts, and you're somehow saying that all given any boundary condition and any matching that is consistent with that boundary condition, you can label it uniquely, using these minimal these sorry these height functions with shifts. Is
Right.
that correct?
With respect to this lemma, you're saying?
Yeah, yeah, I guess that's what I'm trying to parse
Um,
there.
it's not necessarily uniquely, like it's not unique of what we can choose, but um
So like
we
in the picture before, you had this distributive lattice with all of these matchings coming from a particular the slide before, I think, right? Yeah. Like, okay, so those are all of the matchings with a particular boundary condition. And somehow you can label all of those guys in some way with fees. Is that right? Not just the top and the bottom, or the max and the min.
r- yeah, so I can like this isn't necessarily the world of like T mins and T maxes when I step out here. Is that
Well, like, yeah, and the intermediate things, between the left and the right and sides. I mean, somehow you have a way of assigning those,
yeah.
expressing them as T mins of some fees. Is that right?
I'm not sure that I have a way of expressing them as like a T min or a T max themselves, but I do have a way of like describing what the height should be on each face. Um,
Okay.
right, like this isn't because this is kind of the T min height function, but there then what I'm really doing is I'm just changing to get from the top to the second highest. I'm just taking away 7
Seven.
from
Yeah.
that height. And so I can kind of do that repetitively.
Okay. So it's only the min or the max of this lattice that has um, this construction, and that everything else is somehow given uh, by subtracting. Is that right?
Yeah.
Okay.
Yeah. In the same way I could do with this is just adding 7. It's the reverse if I go
Ah,
up from the minimal guy.
okay.
If there are no other questions, I'm going to stop the recording.